So finally, we're at the point of talking about transformers, which is all the latest hotness in machine learning and artificial intelligence. Transformers are the T in GPT and ChatGPT, but GPT and ChatGPT are just specific kinds of transformers, so there's a more general thing to talk about here with transformers. There were ones before this, like BERT, for example, and they have a long history that goes all the way back to auto-completion and machine translation, and even has some roots in robotics and it's things like training AIs how to play video games. The key to the current revolution, though, was something called self-attention, and we're going to go into detail on how that works too. That really unlocked things in 2017. So where did this all come from? So it used to be that natural language processing relied heavily on RNNs, recurrent neural networks, and specifically LSTMs, which is a variation of RNNs. We covered that earlier in the course, but just as a quick review, the key here is that as you process information through a recurrent neural network, that hidden state that comes out the other end gets propagated back into the input for the next time you process it through. And that allows it to maintain information as you process the words in a sentence, for example, or more generally, any time series data. So not only can RNNs be used for language processing, they've also been used for things like, predicting stock prices over time or whatever it might be. But we're most interested in language because we're talking about large language models in this particular section. So you can model a language, a spoken sentence, as just a sequence of words, and you can translate those words into numerical tokens, which in turn can be fed into a neural network of some sort. Neural networks can do this. So we saw in one of our activities earlier in this course that we can use an RNN to do sentiment analysis on movie reviews, for example, and it actually works. So that's pretty cool. However, they have some limitations that have held it back from being used at a more broad scale. In the past, it's been pretty good at machine translation, and the way that it works historically has been through what we call an encoder-decoder architecture. So the idea here of how this thing began was, let's say that you wanted to translate some text from English into Klingon, just to pick a random fictitious language, but it could be French or German, whatever you want, right? So the idea was that we would have these stacks of RNNs on the encoder and the decoder side. So the encoder is responsible for encoding through that recurrent neural network the series of words that are being passed into it. So we pass in the word please, and that gives me some hidden state that's passed into the input along with translate, which represents an updated hidden state that gets passed along to when we process the word me. And when we're done, we have this last hidden state in the middle here that represents where we ended up after processing the entire sentence, please translate me, through those recurrent neural networks. So that is the input that goes into our decoder. So while the encoder is trained to produce a hidden state for English language coming into it, the decoder does the other thing around, right? So it takes that hidden state and tries to produce tokens that, in this case, map to Klingon. So we get that hidden state that is a vector representation of the meaning, if you will, of please translate me. That gets passed to our RNN for the decoder, which then starts to produce tokens. I have no idea how to say that, but in Klingon, apparently that's how you say please translate me. And I think I is in quotes because Klingon probably doesn't really have a word for please. They're not very polite people. Anyway, this creates a bottleneck. That's the main problem here. So we have that one vector tying these two things together. There's only this one hidden state between the encoder and the decoder, and its job is to capture the entire meaning from that entire sentence that went into it. And you can see how that can be limiting, right? We call that an information bottleneck. So because we're passing along this hidden state from step to step as we pass through this RNN, that means that information from the start of that sequence starts to get diluted a little bit over time. And there are some tricks to try to get around that, but at the end of the day, we have this one hidden state that's trying to encapsulate the entire meaning of all of this text. And if you have a lot of that text, that's going to be harder and harder to do, right? Also, it's not terribly efficient either. We can only do this sequentially, right? So we have to process this one word at a time, going through the RNN and doing it over and over and over again, and then passing it to the decoder as another step and decoding it over and over and over again. So this is not very parallelizable the way that it's set up right now. Then in 2017, a revolutionary paper came out called Attention is All You Need, and this came up with a different way of doing things. So now instead of having that one hidden state that encapsulates the entire phrase that you're trying to translate, we're just going with the case of translation here to keep things easy to understand, we now have a hidden state associated with every individual step here. So every time that I hit my RNN with a new word, or a new token to be more specific, it's not just going to pass that hidden state along to the next loop through for the next word, it's going to store that state off. and we're going to keep those states associated with each token around. That way we can deal better with differences in word order, for example, between different languages. So we're not really dependent on the order of the words on how those states get built up. And we can start to have a concept of relationships between words. So let me talk a little bit about this diagram here. So in this example here, we're again translating please translate me from English to Klingon. Let's imagine, if you will, that we've gone through this, okay? So we've said please, it goes through the RNN, and we store off the state at that stage. That then gets passed through again for the next word translate, and we store off that state as well. So for every one of these tokens, we have an associated state that's associated with it. And now as we're going through the translation stage here, through the decoder, let's say that we're at this second word trying to figure out what the next token should be after I, right? So that does not just depend on the hidden state that got passed through from the top here. I can refer to the hidden states associated with each individual word surrounding that token. And furthermore, I can compute weights, so I know that which ones of these states are more relevant to this particular token that I'm trying to translate. And that's the key to it. Because I can compute these weights between different tokens, between different words, that allows me to start to understand what these words mean in context. And that's really a key breakthrough in natural language processing right now. We'll go into a lot more detail on how that works shortly. However, this is still sequential in nature, so you can't parallelize this whole thing. We would like to be able to just say, okay, let's take please translate me and do that whole thing in parallel, right? Like I want to get all these states at once at the end. I should be able to do that, right? If you just look at the diagram, this looks like something you can do in parallel, right? Why not just do please translate and me together? But because they're still based on RNNs, you can't, because this RNN requires the recurrence from the previous stage, right? So we still have to do please, pass that through to the translate, pass that state through to me for this to work. And similarly on the decoder side, we're still passing things down from one token at a time. So it's still not totally parallelizable. It's kind of unavoidable having to generate one word at a time when you're decoding it, but we could at least parallelize this part of it a little bit better. Attention lets you do that. So we're very close to that point now, because now that we have these states broken out per token and we can compute those attention weights per token, in theory, this becomes a lot more parallelizable. So let's make that happen. That's what transformers are all about, right? So the key here is simply that we ditch the RNNs and we replace them with feed-forward neural networks. A feed-forward neural network is just a fancy word for a neural network that goes in one direction. So you put stuff in one end, stuff comes out the other. That's it. And in the case of large language models, these might be very, very, very large neural networks with, you know, 1 trillion parameters or whatever it is. But that's really all they are. Generic deep learning neural networks. That's it. So because we don't have that RNN thing going on here, we actually can do all of this stuff in parallel now. And similarly, we can use that attention trick to parallelize things on the encoder side as well. So as we're encoding what we want to translate, I can also take a look at the context of the other words that are being passed in. So we're kind of making up for the loss of having that sequential processing of the input words from please to translate to me, to having these attention weights that are calculated at each token. So even though I'm not processing those words one at a time in order, I still have information about what other tokens are relevant to this token that I'm processing. And maybe it's a different order. It doesn't have to be sequential necessarily, right? So in this particular case, we're at the point of dealing with me in this parallel operation, and that has an attention weight tied it to translate and a little bit less so to the word please, which would make sense if you think about what's relevant to that particular token. Now, even though this is drawn as though it's doing that one operation, that's just for illustration use. In reality, it would be doing all of these tokens at the same time. Each one of these words, please translate and me, would have its own attention weights to every other token that we're trying to deal with. And that way, we can compute all of these states in parallel without having to do it one at a time, without preserving the order in which we're processing those words. So that becomes a lot more efficient. And similarly, on the decoder side, we also have attention weights that allow us to tie those back together, respecting the context of each token as we go. So that is the fundamental trick of transformers. We call this part over here self-attention. So that's just a fancy word of saying we're computing these weights, these attention weights, between tokens as we go, to allow us to understand what other tokens are important for understanding the meaning of the token I'm currently processing. And because that makes it parallelizable, it means we can train on much, much more data. And that's why this is revolutionary. You know, the idea of self-attention itself is a pretty cool idea, but the real impact is that it allowed us to parallelize the processing, the training, and also the decoding of these large language models much more efficiently. That meant we were able to throw a lot more data at them and do things like throw all of Wikipedia at it, throw all of Reddit at it, and throw all of the books that are out of copyright at it as well, and ultimately have these giant models with over 1 trillion parameters that make up things like GPT-4 and ChatGPT today.